Goldie here, and welcome to our very first video in Unit 4, Probability, Random Variables, and Probability Distributions. This is going to be a video on Notes 1, Basic Probability, and Simulations. If you're new here, I'm Goldie, and I'm here to make AP Statistics easy for you. We're going to go over introducing what probability is, talking about the basics of probability, a lot of vocab surrounding probability, and then an introduction into simulations with probability. So if you are new here, please follow me so you can get all the AP statistics content, and we're ready to get started. So go ahead and grab your notes and let's get settled in and go through this content together.
So starting off with what is probability? Okay, well, probability is all around us, and luckily a lot of you have been exposed to probability throughout your lives so far. In terms of everyday life, games, world events, biology, there's so much that involves probability, and coming up with a definition that encompasses all of the experiences we've already had is going to be kind of our goal today. So you see I have a few examples already written out about what is governed by chance events in our life, because that's really what probability seeks to describe, is chance events. So everyday life, what are some chance events that happen in everyday life? Weather, traffic are a few of the examples I came up with. Maybe you could think of a few more. Games, a lot of the times games involve chance. World events, there's a lot of world events that involve chance, as well as biology and inherited traits. Those involve some chance processes as well. So what is probability? That doesn't really give us a definition, a few examples of chance events, but what exactly is probability? Well, when we do have these outcomes that are governed by chance, what we have found that even though event by event they're governed by chance, through many repetitions, a pattern emerges. And that's a really cool thing, that a pattern occurs even though these events are strictly governed by chance. And math, specifically the branch of math that studies probability, helps us understand these regular patterns that occur. And that's what we're going to be studying. Before we get into the math side of it, though, we have some basic probability terms that I want to make sure I talk about first before I just throw them out there and you have no idea what I'm even saying. So when I talk about a sample space is all of the possible outcomes. You'll hear that we define our sample space a lot, and defining a sample space is just listing all of the possible outcomes of something that you're interested in. And we're going to see a few examples of how we can develop a sample space coming up here. An event is a specific desired outcome or set of outcomes. An event is usually what we are interested in the problem. We want to know the probability of an event. What is the probability that this event occurs? And an event is just a specific outcome in a sample space. Now, the notation we're going to use with probability, it starts off with a capital P, parentheses, and then usually a capital letter inside parentheses, or maybe inside parentheses you might have a word describing an event, but we call this the probability of event A. We would say just probability of event A. Okay, so A, capital A, represents some event. Now this is notation. It's similar to like function notation where we have f of x. You're not taking f times x, it's just a notation and we describe it as f of x. Same thing here, this is probability of A. It is just notation, you are not taking p times A or anything like that, okay? When we talk about the range of probabilities, the range of probabilities means the probability of an event is between 1 and 0. I'll say 0 and 1. Is between 0 and 1. And this is probably something you already knew, but we'll talk about what that means more specifically on the next page. Okay. What does a probability of 0 mean? A probability of 0.5 mean? And then the sum of probabilities. When we list out our sample space and we assign probabilities to each event in that sample space, all of those probabilities are going to add to a single number. Oops, if I can spell probability right. The probability of the whole sample space is 1. Okay. All of the probabilities in a sample space are going to add up to 1. And we're going to see that in the next couple of examples. Now, you guys as a class may or may not have done the intro activity. If you did, awesome. If you didn't, that's okay too. But it introduced two important ideas, this idea of theoretical probability and empirical probability. And I always like using this little picture to kind of describe the difference between the two probabilities. Theoretical probability is your expectation. Right? It's what should happen given your sample space. Or in math notation, and I'll use words to kind of describe this. It's the number of desired outcomes divided by the total number of outcomes. Okay. So an example would be flipping a coin. Right? If you flip a coin, you know that it's 50-50, heads versus tails, which means that if I flipped the coin 100 times, right, that's my total number of outcomes, 100 flips of the coin, how many flips would I expect to be tails? Okay. Well, you would expect 50 out of 100 flips to be tails. That's your theoretical probability. That is the expectation. Your empirical probability is going to be the reality of what actually happens when you either conduct a trial, conduct a simulation, or are working with actual data. Okay? It's the number of successes, divided by the number of trials. Okay, so if I actually sit here and flip a coin 100 times, we know that we expect 50 out of 100 to be tails, but if I end up getting 45 out of 100 to be tails, I'm okay with that. Right? We already kind of have this natural intuition that, yes, we have a theoretical probability, but it's okay to not follow that in the short term. Okay, it's okay for that not to be off. Or excuse me, for that to be off, the empirical probability and the theoretical probability, the expectation versus reality. But we have a fun thing called the law of large numbers. The law of large numbers tells us that the simulated or the empirical probabilities that we have, the more we do it, the closer we get to the theoretical probability. Okay, so if I have 100 flips of my coin and I get 45 tails, that's okay. If I have 1,000 flips of a coin, I expect that to get closer to 50%, to get 500. Oh, I had to think about that. 500 out of 1,000 to be tails. I expect that to get closer to 50% in the long run. Okay, and that's the law of large numbers. It says the more trials you do, the closer the empirical probability is going to get to the theoretical probability. Okay, it's not going to look close when you start off, right? And that's the beauty of just chance behavior or chance events, is that they are very unpredictable in the short term, but in the long term, there's a regular pattern that emerges. So let's go back to this idea that probability is a number between 0 and 1. Okay, so if you kind of picture this almost as a number line, of what I have here. P equals 0. If your probability is exactly equal to 0, that means that the event will not occur. A probability of exactly 0, the event will not occur at all. 0 chance. Okay? If your probability is equal to 1 on the other side, this is the event will occur all the time. This event will occur 100% of the time if it's equal to 1. Okay, so those are your two extremes. Usually, your probability is going to be between these two numbers. Okay? If it's exactly equal to 0.5, which is right in the middle of these numbers, the event is equally likely to occur or not occur. Okay, kind of like flipping a coin. Flipping a coin, it has the probability that I flip a tail when I flip a coin is 0.5. Okay. Now, on the other side, let's do the left side. If I have a probability between 0 and 0.5, that means that the event is less likely. Event is less likely. Okay, less likely to occur. Versus if it's on the other side, between 0.5 and 1, the event is likely. Okay. Now, when we describe how likely an event is, if there's a probability of 0.75 that an event occurs, some people might say that's very likely, where some people would also say, that's likely, but not very likely. You get kind of wishy-washy if you get specific with some of these probability numbers. And a lot of it does kind of depend on the situation as well. But if you think of this number line and think of event less likely, equally likely, or more likely, that's usually a good starting point for understanding the probabilities. Okay. You'll see probabilities written as fractions, decimals, percentages. Usually, we write probabilities as decimals in this class and round to 3 decimal places. Now, that is not a rule set forth by the College Board at all. It's kind of like a rule of thumb, but it's not a set in stone rule, if that makes sense. So I'll round everything to 3 decimal places. If you round to 4 decimal places, or if you round to 2 decimal places, you won't get the problem incorrect by doing that. But 3 decimals, I always say, is just a good, safe bet. Okay, so let's get into some examples. Now, these examples I have here for example 1 and example 2, these are not necessarily AP questions that you'll be asked, but they help you start thinking about some of these events that we're going to be calculating the probabilities of. So keep that in mind here. For example 1, a bag contains 10 marbles of various colors you see there. Question 1, what's the probability you pull out a white marble? Okay, you reach into the bag, you pull out a white marble. So to calculate the probability of an event, in this case, the probability we pull out a white marble, how many outcomes, are there where you could pull out a white marble? Well, there's 4 white marbles, and we divide that by the total number of outcomes. Total, there's 10 different marbles you could pull out. Your desired outcome is the white one. So that's why we take 4 divided by 10. And it's fine to leave probabilities as fractions. It would be more correct to leave it as a reduced fraction, so 2/5. But instead of worrying about reducing fractions and all of that, this is why I just like writing the decimals. Okay, so 0.4. What's the probability you pull out a blue marble? Okay, same thing. Your desired outcome is 3. You have 10 total outcomes, so that's going to give you 0.3 probability. Okay, simple probability. Same thing with a spinner. So each wedge is equal in area. What's the probability that the spinner will land on a red wedge? So if your copy is black and white, I'm sorry, that's a little annoying for you, but I get it. So these are the 2 red ones right here. There are 2 red wedges. Out of a total of, count them up, there's 8 wedges that the spinner can land on. So this has a probability of landing on a red wedge of 0.25. Okay. Yellow wedge, same thing. There's 3 8 spaces. That has a probability of 3.375. Okay. So yeah, not necessarily AP level, but to get you thinking about how we calculate these probabilities. Okay. Now let's introduce the idea of a complement. A lot of the times, a complement is actually easier to find than the actual event itself. And I'll show you some examples of this because it almost sounds like it doesn't. But the probability that an event does not occur is 1 minus the probability that it does occur. Okay. So in symbols, the probability that not A occurs is equal to 1 minus the probability that A does occur, which we use probability of A. Okay. Now, not A, N-O-T-A, the symbol for that is A with a superscript of C. Okay. Some people, I had professors use like an apostrophe sometimes. They had some other symbols as well, but A with a superscript of C has been adopted by the College Board for that. So the probability of not A, or A complement is what the C stands for, is equal to 1 minus the probability of A. Okay. So the probability that it does not occur, 1 minus the probability it does occur. Okay. So let's do a third example. And we're going to use the idea of a complement in one of these problems, okay? So let's say a coin is flipped 3 times, and we record each flip, okay? So first, draw a sample space. Okay, so here's an example of where you might have to draw out a sample space to help you answer the question. So draw out the sample space, meaning draw out what could possibly occur with each when a coin is flipped 3 times. I say each when a coin is flipped 3 times. But for instance, you could flip a coin 3 times and get 3 heads. That is one possible outcome. You could get 2 heads and a tail on the third flip. You could get a head on the first, tail, head, head. You could get 3 tails in a row. Tail, tail, head, tail, or head, tail, tail. Okay. And I hit all of them, okay? 8 possible outcomes when you flip a coin 3 times. There's no other possible outcome. There are only these 8. So the question, what is the probability that when you flip a coin 3 times, you'll produce exactly 1 head? Okay, now 1 head, where does 1 head occur? 1 head occurs here, here, and here. So there's 3 outcomes where I get exactly 1 head. So 3 outcomes out of 8 total. So the probability I flip a coin 3 times and get only 1 head, 0.375. Okay. Part C, what is the probability that a series of 3 flips will produce at least 1 head? Okay. At least 1 head. And this is where I'm going to use the idea of a complement. Now, I'm going to really draw your attention to that keyword at least. Whenever you see that keyword at least, I want you to use a complement, because usually, and I don't want to give a percentage here because we're already dealing with probability, but usually when we have at least, that means that the complement is going to be easier to find than the event itself. Here, it's kind of either way, so let me show you the complement first. The probability of at least 1 head, and I'll use some words here. The probability at least 1 head, using the idea of a complement, is going to be 1 minus, what's the opposite of at least 1 head? Okay, and that's when you use the idea of a complement, that's where you have to think. What's the exact opposite of at least 1 head? Well, it's no heads. Okay, no heads. So if I take 1 minus, and then how many of these outcomes had no heads? Okay, so I'm going to erase my red here. How many of these outcomes had no heads? Just 1, right? That was the outcome that had no heads. There was only 1 out of 8 which means that the probability of at least one head, 1 minus 1/8 is 7/8, or 0.875. Okay. Now, what you could have also done, instead of using the idea of a complement, was, okay, at least one head. This has at least one head, 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 at least one head. 7 out of 8 outcomes. You could have also calculated it that way, okay? But the complement, you only had to find the probability of no heads. You didn't have to take into account the probability of 3 heads, probability of 2 heads, probability of 1 head. You didn't have to look at all of those outcomes, okay? For a small example like this, not a big deal to count those outcomes. But when you get into larger examples, using the complement, it's easier to find that probability that results from the complement most of the time. Okay, we'll practice that a little bit more in the homework. So remember this, probability answers the question, okay, oops, I'm still on red, that's okay. What would happen if I did this many times? Okay, probability is always the long-term pattern. Okay? It's the long-term pattern of what we would expect. We try to use it to predict the short run, but it doesn't guarantee a short run prediction. That's where kind of the myth of law of averages comes in. Now, the law of averages is not a thing, right? It's a myth. But our intuition is a little skewed when it comes to probability, which is, I think, a lot of the reasons why students sometimes struggle with probability, okay? Probability is randomness is predictable in the long run, okay? That's the big idea. We can predict things long term. We cannot predict in the short run. We can try, and we do most of the time, but it doesn't always work in the short run, okay? Future outcomes are not affected by past behavior, okay? It does not tell us what would happen in the short run, okay? So let's say for this, I flipped a coin 10 times and it was heads every single time. My next flip, it'll be more likely that I get a tail, okay? This idea is totally false, okay? That's the myth of the law of averages that a lot of people have in their head. Okay. Yes, flipping a coin, it's 50-50. In the long term, we would expect 50% heads and 50% tails, but not in the short run. Okay. That 11th time I flip, it is still 50-50, right? The coin doesn't have a memory. It doesn't know what happened before it, and it's not going to be affected by those past events that have happened. So don't believe the law of averages. Probability is long-term pattern. Okay. Another way that we ask probability questions is through a frequency table. Okay, so we were introduced in frequency tables back in Unit 2, when we discussed the 2 categorical variables. Okay, so now we're going to use that same idea and use frequency tables to find and interpret probabilities. Okay. So this Example 4, a group of 50 high school students were interviewed and asked what their favorite leisure activity is, okay, from these 3 choices. So between males and females, they could choose dance, watch and play sports, or read, okay? So we want to use the table to find and interpret these following probabilities, okay? So the first one, A, of all the individuals surveyed, so all the individuals surveyed, there were 50 of them. What is the probability of picking a male whose favorite leisure activity is dance? Okay. So male and dance, there were 2 outcomes, 2 people who were male and chose dance as their favorite leisure activity. Of all the individuals surveyed, there were 50 of them. Okay. Total possible outcomes. 2 divided by 50, that's 0.04. Okay. Of all the individuals surveyed, what is the probability of picking a person whose favorite leisure activity is reading? Okay? So the only thing is it's just reading. Okay, didn't say male or female, just reading. That's when we look at the total. Okay, 16 people chose reading as their favorite leisure activity. So that's going to be 16 out of 50 for a probability of 0.32. Of all the individuals surveyed, what is the probability of picking someone who does not consider dance their favorite leisure activity? Okay. So here we can use the idea of a complement, okay? Not dance. Probability that they don't consider dance their favorite leisure activity is 1 minus the probability they do consider dance. Okay. The probability that they do consider dance, there's 18 out of 50 that consider dance. So 1 minus 18 out of 50, 0.64. So I use the idea of a complement to answer this question. You could have also just used the table. The probability that you choose someone who does not consider dance. Okay, well, these are the two categories that do not consider dance to be their favorite leisure activity. Okay, 16 plus 16 is 32, and then 32 divided by 50, that would also give you 0.64. Okay, last question here. Of all the females surveyed, what is the probability of choosing a female who likes reading? Okay, so here, the start of the question changed. Of all the females surveyed, okay, so not everyone in the table, not all of the individuals surveyed, but of all of the females surveyed, what is the probability of choosing a female who likes reading? Okay, so first, female who likes reading, there's 8 of those. But now our sample space has changed. Now we're just interested in all of the females surveyed. So we're going to change our total to 30. Okay, out of all the females surveyed, there were 30 of them. So 8 out of 30, 0.267. Okay. Awesome, and we've reached our last page where we're going to talk about simulations. So we already kind of ran a simulation. If you did the intro activity, you got your first taste of a simulation there. But simulation is going to be the imitation of chance behavior based on a model that reflects the situation. Okay? This is the definition of what a simulation is. Okay, so we're modeling and conducting almost an experiment in a way, without actually doing it. Okay, so what do I mean? Here's an example of where we can use a simulation to help us answer a question. What is the probability that a student gets 6 out of 6 questions correct on a true-false quiz written in Greek, assuming that the student does not know any Greek here, okay? So if you basically have to completely guess on a true-false quiz, you would be looking at a 50% probability, right? There's a 50% chance you get it correct and a 50% chance you get it wrong on any single question. This student got 6 out of 6 questions correct. Should the instructor be concerned about cheating? Perform a simulation using the 4-step process to answer this question. Okay, and that we are going to do. So our 4-step process is basically a way for us to communicate to the reader what our question is that we are trying to answer. We're going to write up a plan so that if the reader were to read this, they would be able to follow the plan and do the same thing based on our instructions. The do is where we're actually going to record simulation data, and conclude is the answers we're going to draw from our simulation. So we're going to use this example here. So in the state part, the first thing you want to do is just state what question you're trying to answer. Okay, what we're trying to investigate here. Is it possible to guess on a true-false quiz and get 6 out of 6 questions correct? Okay, is it possible? Okay, well, let's run a simulation to see. Okay. Now, to run a simulation, we are not going to sit down and take a bunch of true-false quizzes in Greek. Okay? That is a little impractical. So to answer this question, we are going to do a simulation, which means we're going to use a tool of chance to help us model the 50% probability. So the tools we could use coins, dice, table of random digits, or a random number generator, or really anything. Like you can involve spinners if you really wanted to. But we're going to use something for this example that's a little bit more convenient to us, and that's going to be a random number generator. Okay. So here's how I would want you to describe the plan. Okay. So when guessing on a true-false quiz, we would expect the student to get 50% of the questions correct. Okay, and we talked about how that's the theoretical probability, but we know empirically in practice, that's not always going to be the case. Okay? So that's just what we expect. Now, what we expect, that theoretical probability, that's what we're going to base our tool off of. Okay, so my tool is a random number generator. So I'm going to say using a random number generator. Okay, let's say a 1 is getting the question correct, and a 0 is getting the question incorrect. Okay. Now, in your plan, you could use anything. I mean, you could have used, I'm going to flip a coin, heads as they got it correct, tails as they got it incorrect. You could have used a table of random digits and, assign the digits accordingly to a 50% probability, right? It is up to you when you're conducting the simulation, right? This is what I'm going to do, okay? Then I'm going to say, I will randomly generate six numbers, and by six numbers, they're going to be 0 or 1, and count how many are correct. Okay, basically counting how many ones I got, right? Now that randomly generating six numbers, that's going to count as one trial. That's going to count as one test, okay? So I'm going to communicate that. This will count as one trial, and I will repeat this now, how many trials should you repeat it for? Usually they'll tell you in the problem. Kind of a rule of thumb is at least 20 trials. So that's what we'll do here. But you can do however many trials you want. Okay. It kind of depends on what your tool is. A random number generator is pretty easy to use. If you were flipping a coin, that would be much harder and that would take a lot more time. But usually 20 trials is a good simulation run. Now the do part, okay? We're going to record the simulation data. So before I show you how we'll use a random number generator, let's make a little table here, okay? So questions correct and number of trials. Okay, so when I run a trial, which is generating six numbers, I'm going to count how many questions I got correct on my quiz. The outcomes, I could get no questions correct. 1, 2, 3, 4, 5, or I could get all 6 questions correct. And when I say number of trials, I'm going to tally up how many questions I got correct. Okay. So if you want to pull out your calculator, okay, You can do this with me if you want. The TI-84, or here you can see the TI-84 Plus. What we're going to do is use the random number generator on our calculator. So if you probably have seen that before based on an activity we did in the last unit, but if you haven't, you're going to go to Math, okay, and you're going to go over to PROB, okay, and you're going to go down to rand int number 5. Okay. Go ahead and click enter. All right, and it's going to ask for lower, upper, and then an N. Okay, your lower is your lower boundary, and your upper is your upper boundary, and it includes whatever you type. So if I type lower 0 and upper 1, that means it's going to give me the integers between 0 and 1, including the endpoints. So this is just a fancy way of saying it's going to give me a random number, 0 or 1. N is how many numbers I want at a time. And I want 6 numbers at a time to represent the 6 questions on my test. I'm going to click paste. I'm going to click enter. And you can see it gives me 6 numbers, randomly 0s and 1s. Okay, so I can count there. I have 4 1s, okay, which means I got 4 questions correct since 1s represented getting the question correct. So I'm going to go back over and I'm going to put a little tally on 4. I'm going to do this again. I can just click enter again and it'll regenerate the numbers. This time I got 3. So I'm going to put a little tally on 3. And I'm going to keep doing this. This time I only got 1 question correct. Okay. And I'm going to keep doing this for 20 trials. Okay. So if you want to pause and do this yourself for 20 trials, or if you would just like to keep playing and see what I got, I got 1, 2, 3. Okay, when I ran this, these were my results. Okay. So those were my results. Now, if you run the simulation on your own, you would probably get different results, and that's okay. When we conclude here and answer our question, we want to base it off of whatever you got based on your simulation. So your answer might be different from someone else's answer, just depending on how the simulation was run. Okay, so we would start this by saying after conducting the simulation, we see that we had, and this is just me based on my data, I had no trials where I got all 6 questions correct. We had no trials where a student got 6 out of 6 questions correct. So should we be suspicious of cheating? I would say yes. We should be suspicious of cheating. Okay, because in our simulation, we got no trials where they got all 6 questions correct. Now, in your simulation, you might have gotten that, okay? And if you did, acknowledge that in the conclude and say, we got 1, 2 trials where a student got all 6 out of 6 questions correct by guessing, so we are not suspicious of the results. Okay. The conclude is very much based on what you get from the simulation. And again, that might be different from person to person. Okay. And that's kind of a shortcoming of simulations, which is why to answer questions like this that I just posed, we have different probability models to tell us our answer. So we're going to be visiting a question very much similar to this when we get closer to probability distributions. But for now, we answer it with a simulation and conclude with what we found in the simulation.
And that wraps up our lesson on Introduction to Probability and Simulations. Thank you guys so much for following along. If you have enjoyed this video, please hit the like button and subscribe to my YouTube channel for more great AP statistics content. Until then, I wish you endless statistical success, and I will see you in the next video.